Hello everyone, thank you for viewing. This is the first of what might be 3 or 4 videos reviewing the practice unit exam on mole ratios, stoichiometry, and types of chemical reactions. Because the concept of the mole is so controversial, so hard to get deep into your thoughts, it is a good idea for you to visit these 2 websites or these 2 YouTube videos to review your understanding. So let's begin. Question 1 reads, given the formula representing a hydrocarbon. Now we haven't gone over what hydrocarbons are yet, but the name rings true. They have hydrogen and carbon. Question is the molecular formula and the empirical formula for this hydrocarbon are. Now please remember, an empirical formula is the formula where the atoms of the compound are at the simplest whole number ratio. The molecular formula could suggest a multiple of that, giving rise to your ability to construct a structural formula such as the illustration above. So the task is count how many atoms of each we have. We have how many carbons? We have 1, 2, 3, 4, 5. We have 5 carbons. How many hydrogens? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10 hydrogens. Building a formula of C5H10. Now, if this could be reduced, that must be the molecular formula, and in fact this one can be reduced to a simplest whole number ratio that is represented by CH2. For every 1 carbon, we have 2 hydrogens. Okay, now which one matches? C5H10 as our molecular formula and CH2 as our empirical. Question 2. Which molecular formula is correctly paired with its corresponding empirical formula? This is no different than question number 1 in that we're looking for an empirical formula which is the simplest whole number ratio and a molecular formula that could be a multiple of that. So taking a look at choice 1, CO, that's a 1-to-1 ratio. Could that become CO2, a 1-to-2 ratio? Absolutely not. So let's get rid of that. That makes no sense. Number 1, no good. Here we have a 2-to-2 ratio, 1-to-2 ratio. They are not consistent with one another. A 6-to-6 ratio and a 2-to-2 ratio. That's looking pretty good. Or a 4-to-10 ratio versus a 2-to-5 ratio. Well, that too is looking pretty good. Well, let's get rid of number 2. That one did not work. Now, what is the difference between 3 and 4? They both have the same ratio. 3 has a ratio of 1-to-1. And choice 4, they both have a ratio of 2-to-5. Well, the difference is this. In choice number 3, 2-to-2 ratio and 6-to-6 ratio are both molecular formulas because they are not represented as the simplest whole number ratio. Get rid of 3. Choice 4, that is your molecular formula. Because it is a multiple, in this case double the amount of the 2-to-5 ratio, so this one is the empirical formula. Now this one starts getting a little trickier. It reads, what is the molecular formula of a compound that has a molecular mass of 54 And the empirical formula is C2H3. Well, the first thing we must do is determine what the mass of the empirical formula is. And we have 2 carbons, 3 hydrogens. Now, every carbon has a mass of 12. How do we know that? Well, we take a look at our periodic table. We see that carbon right here. There we go. One carbon atom has a mass of 12.011 AMUs. But we're not talking about the realm of one atom. We are talking in the realm of moles, which is 6.02 times 10 to the 23rd number of carbons. And when we have that number of carbons, the mass is 12.011 grams per every mole. We're going to simplify things and just call it 12. So let's get this off the screen. There we go. So the mass of carbon is 12 grams per mole, and we have 2 of them. So our mass from carbon is 24 grams per mole. Now hydrogen, on the other hand, the mass is 1, which means our total mass just from hydrogens is 3 grams per mole, giving us a grand total of 27 grams per every mole. Now that's for the empirical formula. We're not looking for that. We are looking if it is the molecular formula. So how does 27 grams per mole relate to 54? And what we would do is 54, I'm going to drop the units because I'm running out of space here, divided by 27 equals 2 times. That is suggesting that our empirical formula would be doubled. Now we can't write it like this, 2C2H3, because that's still an empirical formula. What it becomes is C4H6. Now I suggest that double check your work. After you do this, you should, well, calculate the mass again. And we would have 12 times 4 is 48 plus 6 grams per mole from the hydrogen, and we get 54 grams. So our answer is C4H6, choice 2. Now we're on to question 4. Now this one is a little bit more straightforward. It reads, what is the gram formula mass of Ca3PO4 2? Now this one might be a little bit easier if we were to write them individually, because there are so many different atoms represented here. Here we have calcium. Now calcium's mass is, let me show it to you here. There she is, right here. 40.08 AMUs, but we're talking in the realm of gram formula mass, talking about grams. We must be talking about moles, so it is actually 40.08 grams per mole, and we are going to use that as our number. Well, we'll round it off to 40. Okay, 40. I don't like how that looks. There we go. 40 grams per mole. All right, now how many do we have? This shows right here that we have 3 of them. Okay, so 40 grams per mole, and we have 3 of them. So our total mass from calcium is going to be 120 grams per every 1 mole of this substance. Now, let's take into account the phosphorus. Phosphorus, its mass is and while we're here, let's take a look at oxygen's mass too. Phosphorus's mass is right here, 30.97. We'll round that to 31. Oxygen's 15.9994. We will round that to 16. So remember 31 and 16. All right. So 31 grams per mole. How many do we have? We have one phosphorus here, but it is being affected by the 2 outside the parentheses, therefore making it 2 moles of phosphorus. 31 times 2 is 62 grams per mole. Now lastly, oxygen. This is where many people make a mistake. How many oxygens are there? So how many moles of oxygen? It shows inside the parentheses we have 4 moles of oxygen, but that is being affected by the 2 outside the parentheses, giving us a grand total of 8. Now we have 16 grams per mole times, as we said, 8 oxygens, giving us a grand total of, well, 16 times 16 is 32. 32 times 32 is 64. I'm sorry, 32 and 32 is 64. 64 and 64 would be a grand total of 128 grams per mole of oxygen in this substance. Add up all of those masses and we get 310 grams for every 1 mole of this substance. Look at the possible choices and there it is. This is a very similar question. It reads, the gram formula mass of NH4Cl is, now let's remember, nitrogen, hydrogen, and chlorine, and take a look at their masses. So that was nitrogen. Nitrogen is here at 14. Let me point it out to you. At 14. Chlorine is here at 35. It's 35.453, so it rounds down to 35. So we have 14, 35, and hydrogen is over here at 1. So we have 14, 35, and 1. Clear. Okay. So nitrogen, its mass is 14 grams per mole, and we have 1 of them, so 14 grams for every mole. Hydrogens, it's 1. I'm going to use a ditto sign so I don't have to keep on writing the units. And we have 4 of these hydrogens, giving us a grand total of 4 grams per mole. And chlorine, we did say that that mass was 35 grams per mole, and we have 1 of them, giving us a grand total of 35 grams per mole. Add them together, 9, 13, 53. Now if I inspect these choices here, I notice that I do have a 53.5. What that would suggest to me is that perhaps they did not round these numbers. Let me show you which numbers I'm talking about. Perhaps when they used these numbers here, they didn't round them. So if I were doing this question on an exam and I noticed this, I would actually roll back into my calculations and I would use the numbers that are not rounded, and lo and behold, the answer would end up being choice 3. It would confirm.